This is the third video in my set of videos on annuities. I do have more videos on other topics in financial math after this, but this is the last one on annuities. And what I have here are two things. I have a couple of Python programs that I wrote, and I just want to go over the graphical user interfaces in terms of how to make use of those. So I'll give you some examples. And then I have a collection of exercises at the end of this lesson, some of which can be solved using the programs that I'm going to talk about. On this slide, I have a little more detail concerning what's in this video. So as I mentioned, there's two Python programs. The first one is Block Annuity Calculator, that's the name. And it can actually work in blocks, but also without the blocks, just simple in general annuities. So that'll be one thing you can click on, and I'll show you what the GUI, graphical user interface, looks like. In that case, you just accumulate money into an annuity, and then it computes the amount you have at term. And then the second aspect of this program is block annuities, where you can have different interest rate and a different amount in each block, and you could have several blocks in your annuity. And that's an option you'll see at the top of the GUI. Then there's a second program, Annuity Payout Calculator. This goes in the other direction, where you buy the annuity for a certain amount of money, like for example for retirement, and then this shows you under a given interest rate and a number of periods how much money you can take out each period. Or you could just put in the initial amount and how many periods you want to have and the interest rate, and decide how much you can take out. So it lets you basically choose all the variables except one, and then it computes the unknown variable. And then, as I said, there's a collection of exercises at the end. A lot of those you can use these calculators to solve. Before I get into the block annuity calculator, I wanted to show you what the input looked like for the blocks. I basically used Excel, and then I saved it as a CSV. And you can see here it's pretty simple. Each one of these represents a block. And the first column are the interest rates. So there's an interest rate of 0.0042, not percentage, but interest rate. If you wanted the percentage, you would need to multiply by 100, and that's per period. So there's 10 periods in this block, and in each period you contribute $500. And then this is the second block. You notice the interest rate is different, the contributed amount is different, and there's in fact 25 periods in this one, and so on. So you could have as many blocks as you want, and the calculator will compute how much money is accumulated in the annuity by the end of the term of the annuity. The annuity calculator has two parts. One is the simple annuity, and the other is block annuity. The simple annuity, you just have a single interest rate throughout the entire time, and the same payment amount R. In the block annuity, you can have different interest rates and payments in blocks, which we'll look at that second. Well, let's first look at the simpler case here. So you put in your interest rate, let's say 5%. Then you can select your frequency of when you're making the payments into the annuity. We'll say it's once a month, and the compounding can be different. We can make it daily, and let's say we want to find the accumulated amount given I don't know, 1,200 per month, and the number of periods. Let's see, we're paying once a month. So if we want to do it for say 3 years, then we can put in 36 here. So we have 5% per year. We put in $1,200 a month. Um, it's compounded daily, and we're going for 3 years. Okay, so that's our solution. Now we can also solve for R or N. So let's clear this. We could do a different thing here. We can put in this. Let's say we don't put in the, let's say we put this in, and I forgot exactly what that was. Well, let's say it was 48,000, and the number of periods, 36, and we left this blank. We left the 0 in here. So it'll tell us how much per month we need to contribute under these conditions. Let me make this the same as before. And yeah, so I didn't exactly put the right number here, but you get the idea. And then you can do the same thing. You can solve for N. So we can leave this 0. Let's see if this works without doing the clear. We should get 36. Yeah, well, it's slightly off because of the rounding, but so I could have also cleared it. So you can leave any one of these 3 blank, as noted up here, and the program will solve for the other, for that one that's left blank. So we'll use this in some of the problems that I have at the end of this section. Then you have the other option, the block annuity, and what you want to do is put your blocks into a CSV file. I've created some examples for you. We'll look at one here. Let's look at this one. I'll give you the link to where these files are. And this CSV file has several blocks, which have, each block has an interest rate, an amount that's being contributed per period, and the number of periods. And the program outputs what you've put in first. So this is actually what's in the CSV file, except for this, the numbering of the blocks. These 3 columns here are in the CSV file. So you have the interest rate, the payment, and the number of periods. Then a different interest rate, number of payment, the amount of payment, and then the number of periods, and so on. So there's 5 different blocks. And then it computes the amount of interest and the payments together for each block. So this is how much you put in and the interest for block 0. This is how much you put in the interest there in block 1, and so on. But this isn't the final amount, because after block 0 is done, this amount of money still earns interest while these other 4 blocks are executing. And this one, the second one here, earns interest while these next 3 blocks are in the process, and so forth. The only one that doesn't accrue additional interest is the last one, since you don't have any further blocks after that. So this second list here is showing you the full amount of the payments and the interest of block 0 all the way to the end of the end of the 4th block, and so on for block 1, 2, and 3. And as I said, this one doesn't accrue anymore because it's the last block. And then all these are added up, and it gives you the final solution here. This second program computes the simple annuity payout. So you put in an initial amount of money, and unlike the other program, the money is being paid back to the purchaser of the annuity until it eventually is depleted and goes down to 0. So we've seen this in the lessons I've gone through previously. Let's look at an example. So let's say you put in $1 million. Then you have the interest rate per period. So let's say it's the period is a month. So we'll put in this here as a rate, not a percentage. And let's say the number of payouts, I don't know, let's put in a big number here, if you wanted to have a payout every month for 10 years, then that would be 120. The amount, let's leave that out. You have to leave one of these blank, so let's leave that out, and let's leave the deferral periods to 0, as well as this number here. I'll show you an example where you have a deferral, but let's just put these 3, and then we'll see how much we can get per month over the 10 years. So we'll compute that. So it's saying we can withdraw $11,102.05 every month for 10 years, 120 payouts, and that'll eventually deplete our $1 million to 0. And keep in mind, when you withdraw this the first time, for example, you're still earning interest on the remaining amount. So it's not you're not staying stagnant. You're making interest on the amount of money that's still in there. So that helps a little bit. Okay, so let's clear this. Now you can also have a deferral. So let's say you retire and your employer, or your savings with your employer is $1 million, but you don't need it immediately because you found a part-time job or a lesser job, so you're going to leave the money in there for a while. But let's say it's the same amount when it's actually getting paid off, and the number of payments, let's do that again, is 120, so we want to leave this blank, but let's say there's a deferral. So let's say you wait 5 years before you start taking any money, and let's say your interest rate is a little bit more aggressive. You're willing to take a little bit more of a chance during this deferral period. Okay, so the money accumulates interest for 5 years, your $1 million, and then at the end of those 5 years, you start taking payments. So let's see what happens in this case. Okay, so quite a bit more. You haven't put any more money into it, but you've accumulated interest for 5 years at a slightly higher rate per period. And instead of a little over 11,000, it's almost 16,000. Okay, so I have a number of examples that apply to the 2 previous annuity lectures. The first one is Mr. Periwinkle agrees to purchase an annuity from a bank. This is intended to be a savings plan. He is to deposit $750 at the end of each month for 5 years with a guaranteed nominal annual interest rate of 3%, compounded monthly. How much is Mr. Periwinkle's annuity worth at term? So the hint here is to use the block annuity calculator, and I'll give you the link to where all these calculators are. And then select the simple annuity option, and then just plug in the numbers given here, and you'll get your solution. The second problem is a continuation. Let's say that the term and interest rate is the same, but Mr. Periwinkle asked the bank how much he would need to save each month to reach $50,000. It turns out the answer, and number 1 is a little bit less than $50,000, so maybe he's interested in this particular number. So either you can use the formula that we developed several lessons ago and solve for R, in other words, the amount he needs to deposit monthly. S is the 50,000, and I is the interest rate per month. So you need to divide 0.03 by 12, just as a caution when you do this calculation. Or if you don't want to do it manually, you can use the block annuity calculator, Again, you would use the simple annuity option, and you would fill in all the attributes except for R, and it'll solve and give you this solution here. So it's a little bit more than this number. Then we have a third problem on this slide. Joan and John Song are saving for a down payment on a house. An investment company has offered them a savings annuity that pays a guaranteed nominal annual interest rate of 3% for the first 30 months, compounded monthly, which may change depending on market conditions for the remaining 30 months of the annuity. However, it is guaranteed that the interest rate will drop at most 0.5% during the second 30 months. The couple would like to know how much the annuity will be worth at term, so in other words, 60 months, if they invest $1,000 per month, assuming the least optimistic interest rate. So in other words, let's say it drops down to 2.5. So you have 3% compounded monthly for the first 30 months, and then 2.5 for the next 30 months. And this can also be solved using the block annuity calculator. In this case, you would need to select the block annuity option, and then you need to create two blocks. And when you feed that into the program, you'll get this as your solution. Okay, and I even created the CSV file for you. If you look for this file in the same directory that has this calculator, again, it'll be on GitHub, and I'll give you the link. You can just open it up, have a look just to see what the blocks look like. You can play around with it if you like, and change the numbers. You can see what happens if maybe it actually increases to say 3.5%, and just download this file and change it locally, and then feed that in and see what result you get when you have in 3% and then say 3.5. Of course, it'll be more than this number. Okay, so I have quite a few more problems, and I'll continue on the next several slides with those. So continuing with the previous example, assume the songs really needed $75,000. If we assume the terms are the same as before, so in other words, 3% annual for the first 30 months and 2.5% annual percentage for the second 30 months, what would they need to do in terms of their savings on a monthly basis in order to reach the 75,000? So there are different solutions. There's an infinite number of solutions, really. They can increase the amount on the first 30 months, or they increase the payments on the second 30 months, or they can do many combinations of the two. I just took one approach here by fiddling around, and I was using the calculator, and I was able to find something that got them to a little over 75,000. So my approach was to increase the payment amount in the first block and leave the payment amount in the second block at $1,000 per month. I used the block annuity calculator and experimented with various payment amounts for the first 30 months. When I got to $1,333 for the first 30 months and $1,000 per month for the second 30 months, then the final accrued value was a little over 75,000, which is what we're looking for. And just one caution and sort of an apology too. The calculators I developed, I mean, they're not, as you can tell, they're not production quality. They're just something I did to help out with the doing some of the calculations here. And sometimes I use interest rate, and sometimes I use interest percent, and you need to do those. You need to follow those exactly because you'd be off by 100 in either case. Now this particular block annuity calculator was expecting rates, monthly rates. So you have to do a bit of a conversion here. So you have your 3%, and first you need to convert that to 0.03, and then you need to divide by 12 to get the monthly rate. So that would be 0.025. And then you need to do the same deal with the 2.5%, and that gives you this monthly rate. Okay, so just as a warning, if the numbers are coming out wrong, make sure the calculator is asking for a rate or a percentage. Some of them are just percentage, which is a little bit easier to enter in, but as I say, I wasn't consistent, and sorry about that. Then the second example on this slide, problem number 5, we have an ex-professional athlete, Mr. Trubisky. He has $10 million. He's just retired, and he wants to invest half of that in an annuity, and he'd like to take out $50,000 per month, and the annuity is going to pay him 3% nominal annual interest rate. So in this case, I would suggest using the simple annuity payout calculator to see if how long this would last if he's withdrawing at $50,000 per month. Then the related problem is after doing the computation, Mr. Trubisky, and also you if you work this, realizes that his withdrawal amount will last about 9.6 years. So given that he's only 35 years old, he wants to pay out to continue for 50 years and not just this shorter amount of time. So the question is, well, given the same interest rate, the 3% compounded monthly, how much would he be able to take out on a monthly basis if he extended this for 50 years? And if you use this calculator, you'll see it's around $1,698.87 per month. So quite a bit less, but on the other hand, he's getting it for 50 years. Then one last problem on this slide. How can the block annuity calculator be used to calculate an annuity due? Right, that's when you make the payments at the beginning, where the payments are made at the beginning of each period. And there is one accrual period after the last payment. So we want to kind of stretch, I guess you would say, the capability of the block annuity calculator to actually do annuity dues. And the hint is use 2 blocks, with the second block consisting of a 0 payment at the same interest rate. And I'll explain why that works on the next slide. And then the slide after that, we actually have a specific problem asking for the calculation of annuity due, and we can use our approach here, which again I'll explain on the next slide. Here's the explanation. The block annuity calculator computes each block's value using the ordinary annuity formula. It assumes that the payments are made at the end of each period. Block 1 with parameters I, R, and N. This is the first row in our CVS file. Therefore produces this value. The S sub 1, the sub 1 here is just referring to the first block. And so this value here is the accumulated value of an ordinary annuity, not an annuity due, at the end of period end. Adding block 2 with these parameters, I, 0, and 1. So the same interest rate, but 0 contribution, and then just 1 period, does 2 things. Its own accumulated value is 0, since the payment is 0, and it compounds block 1's value forward by 1 additional period. Right, there's this 1 period here. The total at the end of block 2 is therefore 1 plus I times this formula here, which gives us this, which matches the closed form expression for the accumulated value of an annuity due. So you basically just shifted things, giving them one additional period of interest accrual. So intuitively, the zero payment block shifts each of the n ordinary annuity payments forward by one period, which is algebraically identical to moving every payment from the end of a period to the beginning. Okay, so kind of clever to be able to do annuity dues without creating another calculator and just using the block annuity calculator. And I'll have an example on the next slide, the first exercise actually on the next slide, that'll give you an opportunity to test this approach. Problem number 8 is a test of our methodology that we just talked about. We want to find the value of an annuity due at term given the following conditions: $150 payment at the beginning of each month for 4 years at a nominal annual interest percentage of 6% compounded monthly. So we can do it manually using the formula for annuity due. I would be 0.06 divided by 12, or 0.005, so that we get plugged in here. R is 150, and N would be 4 times 12, 48, and you should get this number here. Or you can use the methodology we talked about, where you take the block annuity option of the block annuity calculator, which I'll make available to you. I'll give you a link to where this program is, and I'll put in the information to the video. And then you can use this input file. It has 2 blocks based on the methodology we talked about. And this file will also be in the same directory as the calculator. And you just plug that in as input and you get the same answer. Then we have this problem with number 9. Milton invests $75,000 in a deferred annuity at a nominal interest percentage of 4% compounded monthly. The annuity is deferred for 5 years, and then after there's 90 monthly payments made to Milton. And you want to compute the amount of the regular payments. So just to recap, the $75,000 earns interest, 4% compounded annually, compounded monthly, for 5 years. The money's not touched, it's just growing. And then 90 monthly payments. So even then, whatever's left of the $75,000 continues to grow over the 90 months until you deplete it. So here we would use the deferral option. There's 2 fields in that calculator, simple annuity payout, for deferral. And you get this solution here. And again, you need to be careful converting this to a rate. You need to take the 0.04 divided by 12, and you get a repeating fraction. The temptation is to truncate that at like 4 or 5 or 6 places, and if you do that, you'll get something slightly different than this. So when you're compounding something, for this many periods, for 5 years every month, and then another 90, even a small truncation can lead to dollars worth of errors. And I'll give you an example. Actually, I'll use this example in the next slide to show you how you can mess things up by rounding off. Then in a variation of this problem, let's say that we don't know what the initial amount is, but Milt wants to get payments of $1175.50. Maybe that's the amount of his monthly rent, and he would like to know how much does he need to invest in a deferred annuity under the same conditions, 5 years deferral and then 90 monthly payments. So you can use this calculator again, the simple annuity payout. You just leave blank the initial amount, the purchase amount, and you fill in the payments amount, you put in the deferral, the number deferral periods, the number of payment periods, and you get a slightly smaller number than the 75,000, which makes sense since this is slightly smaller than this number here. Then I have one more problem, which I almost removed. This was here when I wrote the book on which these videos are based several years back. And in the meantime, I've upgraded this simple annuity payout calculator to support deferrals. But initially, I had a separate calculator just to deal with deferred annuities. And the one thing, I left this in the same directory with these other programs. So if you want to play around with Python programming, and you can take this calculator and update it to support the case where the interest rates during the deferral, in other words, for example, the 5 years here, is different from the interest rate during the payments, in other words, the 90-month period in this example. And you already have the code that does that here in this program. So you can try it on your own first, and then if you get stuck, you can look at the code from this calculator and play around with it. But again, it's more if you're interested in Python. It kind of goes a little bit outside of just the financial math. It's more of an exercise in Python programming. On this slide, I wanted to talk about the truncation error that I mentioned. So rate precision does matter. And if we look at the specific example we had, was the deferred annuity payout, with 75,000 being the purchase price, 4% annual, compounded monthly. So here's the problem. When you convert from the 4% to the monthly rate, you have to divide 0.04 by 12, and you get 0.0, and this 3's repeat indefinitely. And the temptation, and I made the mistake, is just to go into your calculator, so you have the 4%, and you convert it just so you can put it into either my calculator or someone else's calculator, and you figure, well, this is close enough, right? It's all the way out to 6 decimal places, and you do the computation, and you're off by 4 cents, or roughly, a little over 4 cents. And then maybe you go to the formula, and instead of doing this, you do it on the spreadsheet, and you put in 0.04 divided by 12 for I, and the spreadsheet goes out to whatever 16 decimal places, and it actually gives you the exact, or close to the exact answer, 42 cents, and you're into the less than cents at that point where the error is. So the lesson here is, if you're working with any calculator, not just the one I wrote, and it's asking for a rate, and what you have in hand is a yearly percentage, and you go ahead and do it on your calculator to insert that input value. Take as many digits as the calculator will give you, and will fit into the input window to make sure you don't have these rounding errors. Okay, so that's the lesson, and it'll save you some grief if your numbers aren't adding up. The problem is these numbers here, the M and the N. We're talking about 60 and 90, and when you take a number like 1 plus 0, 0, 3, 3, 3, 3, whatever, and raise it to such a high power, you're going to get eventually more and more variance from if you're rounding based from what the actual number is. So just something to be aware of. There are 2 more problems in this lesson. First one is compute the accumulated value of a general annuity with term 13 years where the interest is compounded 7 times per year at a nominal annual interest rate of 7%, and payments into the annuity are made 23 times per year in the amount of $500 per payment. So we derived the formula for dealing with this, where the compounding period, number of compounding periods and the number of payments were not the same. And so we want to convert this 7%, we want to convert this to a rate, which I've done here, 0.07 divided by 7, right? It's 7 times a year. And we want to find the equivalent rate if we do it 23 times a year. And that was this formula. And you can compute this in a spreadsheet. I would take 7 divided by 23 on one line and then raise 1.01 to that power and subtract 1, and you'll get this. And then we just take this value and use the formula for the accumulated value of a simple annuity with period interest rate J, this number here. Number of periods would be 13 years times 23 times per year, so 299. We're given the payment amount, 500. And if you do that calculation, you can check it with using the block annuity calculator with a CSV file having a single line, the interest rate, J, the amount of payment, $500 per period, and then the number of periods. And then the final example is compare the present value of an ordinary simple certain annuity with 360 equal payments of $2,000 at an interest rate of 0.005 per period with a continuous annuity of same term, payout, and interest rate. And I'll give you the answer here. So they're almost the same. For the first case, you get $33,583 and 23 cents. And for the second case, you get slightly more, $334, $416 and 49 cents. Okay, so that was the last exercise in this lesson. And this is the last lesson I have on annuities. I'll follow up with several lessons on the repayment of loans, including mortgages and balloon loans. And then I'm going to prepare some lessons on bonds, and then some lessons on capital budgeting, and then that'll be the end of this series. So if you like the series and if you like this lesson, please give it a thumbs up and stay tuned for additional lessons.